All right, guys. In this video, I'm going to be going over Fairfax County Public Schools Unit 2 practice assessment that we have. So hopefully if you're watching this, you've gone to your chemistry SOL prep folder, you've gone to the FCPS county assessments, and you've done this Unit 2 practice. Okay, so in this video, I'm just going over the answers to this practice assessment. And then after you watch this video and you understand everything you might have missed, then you should then try this assessment, but take it kind of in SOL format, meaning only a periodic table and only a calculator, no formula sheet. And anytime you feel like you needed a formula sheet to reference how to calculate something, make sure you make a note of that, write it down on the cheat sheet you're making so that you can memory dump on the day of the SOL. You can take that scrap sheet of paper and you can turn it into your own quote unquote cheat sheet, but really it's just your formula sheet that you're recreating from memory, which you're allowed to do, and you should definitely do it. It'll minimize mistakes, and again, it'll get you 3 to 5 questions better than what you would have done if you didn't do the memory dump. So really I can't suggest that more strongly. Okay, so make sure you do it. All right, so again, I'm kind of going to go back and forth from the assessment here in Schoology to my notes on the question. Just, hopefully it'll help you review. Okay, so once you submit, you should get the correct answers. But then, and hopefully you understood once you saw what the correct answer was. But if you didn't, that's what this video is for. So if you need to, just skip ahead to the questions that you really need more of an explanation for. You don't have to watch the whole thing. Okay. All right. So question 1, they give us some data. We have 5 different trials. Notice all of our measurements are very close to each other. Each trial, we basically got the same answer. We were a little off here, but pretty on point. And the true value, the accepted value, the actual value is 5.2, and our measurements were 5.20. So our data is looking good. And all this question is asking is basically how accurate are we, how precise we are. Okay. So remember, precision has nothing to do with what the true value is, right? The true value tells you nothing about precision. Okay. Accuracy is how close you are to the true value. Okay. So obviously, all of our trials are very close to the true value, so we're accurate. So high accuracy. Okay. Precision is how close your measurements are to each other. So if you only do one trial, you have no idea if you're precise. You could be accurate. You could do one trial, you could get 5.2, and the actual answer is 5.2. But you need to do multiple trials to know if you're precise or not. Like if trial 1 you get 5.2, and then trial 2 you do the same thing but you get 1.2, you're not precise. So precision is how close your measurements are to each other, how each trial is to each of your other trials. Accuracy is how close you are to what the true outcome should be. Okay. So in this case, we're precise because all of our measurements are close to each other, and we're also accurate because our measurements are close to the true value. So it's high accuracy and high precision. All right. So let's go back to the next guy. We'll go to question 2. So it was high accuracy, high precision. So I got the answer choices kind of scrambled. So it was choice A on my paper copy, but choice C here. Okay. Let's go on to question 2. Okay. So they give us some measurements, and all we're doing is calculating percent error. So this is a great time for memory dump. I'm going to keep plugging that as much as I can because, again, I've seen students who I expect to get past advance not get past advance because they didn't do the memory dump. I've seen students who I didn't expect to get past advance because they did do the memory dump. Again, I'm telling you, it's 3 to 5 questions better if you're just thinking about all that stuff before you read a test question. Do the memory dump. Okay. So remember what percent error is, right? And remember, you don't get this equation. You got to know how to calculate percent error. And remember, it's the absolute value. So you could do the true minus experimental divided by true, or you could do experimental minus true divided by true. The main thing is that you're dividing by the true value. Okay. And understand that you have to do the difference between the two values and you're taking the absolute value. So again, it doesn't matter if you do experimental minus actual or actual minus experimental. That doesn't matter. But what matters is you're taking the absolute value of the difference and then you're dividing by the true value, the known value. Okay, so we got to be able to read the question and realize what was our experimental value versus what were we trying to get, right? So the student measures 303 Kelvin. So that's the experimental value. The accepted value, the true value, is 309 Kelvin. So that's the true value, the actual. Okay. And then also, process of elimination, that's not how you do it, right? That's not how you do it. So it's not B or C. And so this is just making sure you are dividing by 309 and not dividing by 303, right? So choice A, because 309 was the true value in this case. Okay, and 303 was the experimental value. Okay, all right. So let's go on to question 2. All right, if we have 6 valence electrons, how many bonds will we normally form? It doesn't mean always, but normally. All right. So maybe think about an atom that has 6 valence electrons that you're very familiar with, like oxygen. Oxygen has 6 valence electrons, sulfur, but we'll go with oxygen's group, oxygen. And oxygen normally has 2 bonds to it. It might be a double bond, right? Or 2 single bonds, but it's usually 2. So when you have 6 electrons, 6 valence electrons, you usually get 2 bonds. If you have 7, you'll usually get 1 bond. If you have 5, you'll get 3 bonds like nitrogen normally. Okay. So 6 valence electrons, something like oxygen, normally forms 2 bonds. Okay. But again, right, remember, right, any element, if we drew a dot structure of an element that has 6 valence electrons, this is kind of how we draw the dot structure. And it's only the unpaired electrons that usually will form bonds, or those are the ones that will form bonds first. So since I only have 2 unpaired electrons, I'll form 2 bonds. If I only had 1 unpaired electron, I'll form 1 bond, right? Carbon has 4 unpaired electrons in its dot structure, and that's why carbon normally has 4 bonds, okay? All right, let's go to the next one. Okay. All right, so remember, you don't have the back of that periodic table that you normally get for our tests that have a list of polyatomic ions and their formulas and their charges. You don't get that, right? There's 7 to 8 that are really important that we'll be talking about in our meetings that you really want to have memorized. But a lot of times they'll just give you a chart and you just got to know how to use the chart, right? So they're giving you the chart here, okay? Ammonium oxalate, we want to get the right formula. So let's find ammonium, it's NH4 plus. Let's find oxalate, it's C2O42 minus, right? It's an ionic compound, right? A cation and an anion. How do they form? What ratio do they form? It's dependent on their charges. So since the oxalate's 2 minus, but the ammonium's only 1 plus, we're going to need 2 ammoniums for 1 oxalate. So we got to have a formula that shows 2 ammoniums, sorry, I'm saying the word 2 and I'm holding up the number 3. 2 ammoniums, 1 oxalate. So which of those formulas does that? It's this one, right? 2 ammoniums, 1 oxalate. C2O4 is oxalate, right? Okay. But again, let's see if I have any notes for that, right? Do the crisscross, right? Ammonium, NH4, 1 plus, oxalate, C2O4, 2 minus. Maybe put those formulas in parentheses before you do your swap and drop, right? But remember, if a 1 is going outside the parentheses, you don't need the parentheses anymore. So that's why you don't see the parentheses over here in the answer choice, right? All right. Right, and then, process of elimination, if we go back to the question, right? It can't be this one because that has cyanide, right? Cyanide. So it's talking about oxalate. So it's not that one. So we can cancel out that one, right? And if we had to take a blind guess, hopefully we could narrow it to at least 3 choices and not 4 choices. Okay. So we go to the next one. This is just saying, hey, name this compound. Okay. So we got to remember that Na is sodium. If we forget that, remember we have our periodic table to reference to check that out. But then C2H3O2, if we find that in the chart, oh, they didn't write it the same way. They wrote it CH3COO minus. Well, 2 carbons is C2, right? 3 hydrogens H3, and then 2 oxygens O2. So this right here, right, the way they wrote it here is just a different way of writing that formula here. It's the same thing. So we got sodium, and then we got acetate. So the name of this compound is sodium acetate. So let's find sodium acetate. There you go. All right. Right. We know it's not oxalate, right? Because C2H3O2, that's not oxalate, right? C2O4, that's oxalate. And it is something with acetate, but Na is not ammonium. NH4 is ammonium, so it can't be this one or this one. So, hopefully by process of elimination, we eliminate this one, and this one, and what's left, Okay. Move on to number 6. Which of the following is the correct name for the compound MnF2? So we have to remember that Mn is a metal. So this is an ionic compound. So remember to name the ionic compound. Can I eliminate choices? To name an ionic compound, you name the cation, which is manganese in this case, and then you name the anion. F minus is fluoride, right? So this is going to be manganese fluoride. But then the other thing we have to remember about the manganese is transition metal. Remember, it's one of those metals that needs a Roman numeral to identify it in the name. And remember, the Roman numeral goes right after the name of the metal. So manganese Roman numeral, okay? And let's just process of elimination. You've never seen a Roman numeral at the end of the name. You've never seen 2 Roman numerals, one Roman numeral and then another Roman numeral. So hopefully we've eliminated 3 of the 4 choices. So what's left? It's manganese 2. All right. Why is the manganese 2 plus? Well, remember, it's paired up with fluoride. Fluoride is 1 minus, and you have 2 of them. So that means the one metal you have here has to be a total of 2 plus. And since you have one of them, that means it's manganese 2. So manganese 2 fluoride. Okay, so in this case, it was choice B. On my randomized answer choices, it was this one. Okay. And I guess just another note, watch out on the SOL. A lot of times they'll throw in Mn, manganese, or Mg, magnesium, and they look very similar in name and sound very similar in name. So one of the incorrect choices might be magnesium 2 fluoride, and you might click on that accidentally when it was manganese and not magnesium. So watch out for little things like that. Right? Okay, here they give us the name, we want the formula. So anytime you see a Roman numeral in the name, it's ionic. It doesn't mean all ionic compounds have Roman numerals, but if you see a Roman numeral, it's an ionic compound. So you have an iron 3 plus ion and a phosphide ion. Okay, so we have to recognize that phosphide, ide, it's not a polyatomic. It's not phosphate. It's not phosphite. So it's just P, right? So we'd have to go to our periodic table, see that phosphorus is in a spot that always forms a 3 minus ion. So phosphide is 3 minus. The iron is 3 plus. So if you have a plus 3 ion getting together with a minus 3 ion, they're going to get together in a 1-to-1 ratio. So it would just be 1 iron and 1 phosphorus. And so it would just be that, right? We swap and drop the charges, but then we reduce. So 3 to 3 reduces to a 1-to-1. Okay. Again, put any notes here. I just have to say it was iron 3. How did I know it was 3 plus? They told me. That's what the Roman numeral means. And then what did I reference? I referenced my periodic table. Phosphorus has 5 valence electrons. It needs to gain 3 to get it to a stable ion. So it has to gain 3 electrons. That's why it's 3 minus. So 1-to-1 ratio. Okay. Oops. Where am I going here? All right, let's go to the next one. All right, the formula for aluminum chloride. All right, again, aluminum is a metal, so we have an ionic compound. All right, no Roman numeral. So this is where we have to reference our periodic table. Aluminum is a 3 plus ion, and chloride is a 1 minus ion. So you're going to need 3 chlorides and 1 aluminum, And so that would be this formula. This shows 1 aluminum, subscript 1, 3 chloride, subscript 3, right? Good. All right, so here we have a drag and drop question. So your SOL has drag and drops, okay? And we just have to drag these numbers into subscripts for our nitrogen and our fluorine. And it's got to match this name, right? Nitrogen trifluoride. Remember, we don't use a prefix for the first element if the first element has 1, right? So if it were 2 nitrogens, it would be dinitrogen. If it were 3 nitrogens, it would be trinitrogen. If there were 7 nitrogens, it would be heptanitrogen, right? But if there's just 1 nitrogen, they're not going to say mononitrogen for the first element, right? We say carbon dioxide, not monocarbon dioxide, right? So that means there's only 1 nitrogen. So we'll put a subscript there of 1. And trifluoride, tri means 3, so 3 fluorines. So we'll put a 1 there and a 3 there, and we get our formula. Okay. Now 1 is understood, but not on a click and drag situation, right? On a click and drag situation, you got to put a number in there, and they give you 1 as an option. So go ahead and put in the 1. But if you ever see this formula written out, it's just going to say NF3. It's not going to say N1F3, right? But for this scenario, we needed to know to put the 1 there, okay? We'll move to the next one. All right. So what of these elements represented by X will form a compound with fluorine where it's basically a 1-to-1 ratio, right? 1 fluorine for 1 element of X. All right. So hopefully we can eliminate argon, because argon's not going to react and form a compound with fluorine, right? The noble gases don't really form compounds, right? They're the inert gases. They don't react, okay? So basically, these are different metals. And so which of these metals is a +1 ion? Because fluoride, F, is a 1- ion. And the answer would be sodium, right? Sodium, whoops, I don't want to eliminate sodium. I want to select sodium. Sodium is +1, magnesium's +2, aluminum's +3. So if it was XF2, it would be magnesium because you need a 2+ ion. If it was XF3, it would be aluminum because you would need a 3+ ion. Okay. Number 11. 2 elements in a molecule have different electronegativity values. Which of the following most likely holds the elements together in 1? Okay. So this is when vocab kind of matters. Okay. So molecule is the word we use for a covalent compound, right? If this were an ionic compound, then I really shouldn't say molecule, I should say formula unit. Like sodium chloride is a formula unit, whereas H2O is a molecule, okay? So I know it's not an ionic compound. So I know we're not talking about ionic bonds, so I can get rid of the ionic compound choice, okay? And a chemical bond, when we're talking about sharing electrons, it's not an intermolecular force. So it has nothing to do with that, okay? So remember, electronegativity difference when atoms are sharing electrons will make that bond polar. The more electronegative, the more difference in electronegativity, the more polar it is. If they had same electronegativities, it would be a nonpolar bond, but different electronegativities in a covalent bond makes it polar, okay? So the answer would be, it's a polar, I don't want to do that. I want to select. It's a polar covalent bond because the elements do not share electrons equally because they have different electronegativities. Okay. All right, the dye structure for HCl. So hopefully we can eliminate this one and this one, right? Hydrogen can only have 2 electrons around it. That's the max. All right, so this has hydrogen with 8 electrons around it. This one also has 8 electrons around it, right? Remember, when they're in the middle, they're being shared. So you can think of that, these 2 dots right here as a line, and that's a line, so that would represent a double bond. Remember, hydrogen can't have double bonds, right? And chlorine needs at least 8. So it can't be that one. So process of elimination brought me to this one, right? Let's see if I have some notes on it. Yep. So that single bond right there can also be written that way. Okay, but whoops, right? In this case, that way because the chlorine would need those three unpaired electrons, pairs around it. Okay. All right. Go to the next one, maybe. Here we go. All right. Why is a molecule BF3 nonpolar even though the bonds between boron atom and fluorine atoms are polar? So I have polar bonds, but the molecule itself is nonpolar. Remember, that's about symmetry. If you're asymmetrical, you're polar. If you're symmetrical, you're nonpolar. Even if you have polar bonds. So we know it's not asymmetrical. We're looking for symmetrical or something that kind of means the same thing. Remember, BF3 would be trigonal planar, which would be a symmetrical shape. And so it's nonpolar because it's a symmetrical molecule, even though it has polar bonds. Okay. All right. What is the number of pairs of electrons that are shared? So basically, how many bonds does it have? Is it a single bond, a double bond, or a triple bond? Hopefully you've memorized that nitrogen is the diatomic with a triple bond, right? So it's sharing 6 electrons, so 3 pairs, okay? 6 electrons, triple bond, 3 pairs of electrons, 6 electrons, triple bond. And oxygen is a diatomic with a double bond, and the rest of the diatomic elements just have single bonds between them, okay? But let's go here, right? It's sharing 4 electrons, so that's 2 pairs. What am I doing, oxygen or am I doing nitrogen? This one's oxygen, so I don't know. Let me see. It says nitrogen atom. So now I'm second guessing myself. This is the question I have on the practice one. So maybe the oxygen question is on the actual county assessment. So check that out. But nitrogen's sharing a total of 6 electrons, so that's a triple bond, 3 electrons paired, electron pairs being shared. Oxygen, it's a double bond, so 2 electron pairs being shared. Okay. All right. Hopefully I fixed that. All right. All right. Anyway, next one. Which of the following is the correct molecular shape of H2O? Hopefully you've memorized that. It's bent, right? We use that all the time as an example, right? But, right, even if you made the mistake and drew water like this, we have to recognize that that's not linear, okay? We might draw it that way, but whenever you have 2 bonds and 2 unshared pairs on the central atom, that's the real shape, it's bent. So that bond angle isn't 180, it's really 105, around 109, 105 degrees. All right, remember it's not 90, even though we might draw it and it looks like 90, that bond angle is really, because remember, it's got 3 dimensions for all of these electron domains around the oxygen to spread out all around, okay? All right, let's go to the next one, number 16. Okay, why does sodium chloride have such a high melting point, whereas CCl4 has a very low melting point? Remember, melting point is an IMF question, essentially. But when it's not the same type of compound, then it's kind of about the type of compound you have and the IMFs that they have, right? So sodium chloride is an ionic compound. So remember, they tend to have high melting points because the ionic bond is pretty strong. Okay. And then remember, for covalent compounds, you have hydrogen bonding, which is pretty strong. Then you have dipole-dipole interactions, which are not as strong as hydrogen bonds. And then you have London dispersion forces. What we have to understand about CCl4 is it would be symmetrical, it would be tetrahedral shaped. So the only IMF it has is London dispersion forces. And that's why its melting point is so low. It has weak IMFs, intermolecular forces. So boiling point has nothing to do with mass, okay? It sometimes could have something to do with electronegativity difference, but that's like if you're comparing polar molecules to other polar molecules and how intense their dipole-dipole interactions are. So it's not about that. It's not about number of atoms. Okay. So process of elimination. Now, this is where, again, vocab, matters. Hopefully you've been paying attention in your chemistry classes, but like another way to say ionic bond is electrostatic force, right? The force of opposites attracting each other. And that's what an ionic bond is, a positive ion and a negative ion connecting together. That's the electrostatic force. So electrostatic interactions is the same thing as saying ionic bonds are stronger than the intermolecular forces in covalent molecules. So this is basically ionic versus covalent question, not necessarily which of these covalent compounds has stronger IMFs, if that makes sense. Okay. All right, let's go to, did I say anything in the notes here? Yeah, just electrostatic attractions are ions attracted to each other. So another way to say that, ionic bond, Coulombic attraction, charges attracting each other. Okay. All right. Let's go to number 17. All right, 17. All right. We should, hopefully you can just go bent, trigonal planar, linear, tetrahedral. Boom, 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 boom. It's asking which of these would be tetrahedral geometry. So, all right, right. Remember, tetrahedral, 4 bonds, 0 lone pairs. That's this one. And look at the way, they try to make this a little 3-dimensional here. And notice that bond angle isn't 90 degrees. It's greater than that. Okay. And notice here, water, right? Imagine a lone pair and a lone pair, and that bond angle is still greater than 90, right? This bond angle is around 105, whereas this bond angle is around 109, but relatively the same. This bond angle would be 120, this would be 180, all that good stuff. But again, it's more important just tetrahedral, linear, trigonal planar, bent, right? All right, so here we have an empirical molecular formula question. So we can't really eliminate these because all of these reduce back to this formula, right? So 363 reduces to 121, 484 reduces to 121, 242 reduces to 121, and 121 is 121, right? So all of these could be the answer. The limiting thing, the factor is which of these adds up to 90 grams per mole. So which of these formulas would have a molar mass of 90 grams per mole? And then they would all reduce back to this formula, okay? But only one of them would add up to a mass of 90, right? So remember, the way to do it is find the molar mass of the empirical formula that they gave us. So I added, 1 carbon, 2 hydrogens, and 1 oxygen. That adds up, and I just rounded, right? We can just round here, right? So 12 plus 2 plus 16. So we got around 30 grams per mole. The molar mass of the compound is 90. So if we do 90 divided by 30, that tells us what to multiply our subscripts by. So I'm going to multiply the 1 by 3, the 2 by 3, and the 1 by 3, and I get C3H6O3. So it was this choice, right? May not be the same choice on my actual assessment. It was this one, okay? Empirical formula, all we have to do, 6 to 12 reduces to 1 to 2. So all we have to do is reduce the ratio. If it doesn't reduce, then the empirical formula and the molecular formula are the same thing, okay? But this one, 6 to 12 is the same thing, same ratio as 1 to 2. Okay. All right, this one, they give us all this lab data. It can be a confusing question if we really get into the weeds. We're going to do a hydrate lab, hopefully before the SOL. So hopefully you'll know more about hydrates and that kind of thing. But it's just percent by mass, and it's what percent by mass of the hydrate is water. So a hydrate would be copper 2 chloride with water in the formula. So it would be like CuCl2 with 1 water, or it could be CuCl2 with 2 waters, or CuCl2 with 3 waters, or CuCl2 with 4 waters, 5 waters, 6 waters, whatever. Okay. But this is just saying what percent of the hydrate, that whole compound, is water. And all we have to do is take the mass of the water in the hydrate divided by the mass of the hydrate. And they gave us that number, right? This was the mass of the hydrate. So the CuCl2 with the water. This is the mass of the anhydrate, which would be the CuCl2 without the water. And the difference is the mass of the water, right? So all we have to do to find the percent mass of water in this hydrate is take this mass, 0.96 grams, and divide it by the mass of the hydrate, which was 5 grams, and multiply by 100 to make it a percent. So it comes out to be 19.2. And, this is where you have to read the instructions. It says round to the tenths place. So, maybe if you thought you should only have 2 sig figs, and technically you should because that mass only has 2 sig figs. So you should round to 19, but the rules tell us to round to the nearest tenths place. When I do this in my calculator, I get 19.2 exactly. So 19.2 is what I need to type into my answer here. 19.2. Okay. And notice you don't have to put the percent sign. They put the percent sign there. Okay. All right. Which of the following substances significantly dissolves in water to create a solution? So basically this is asking which of these is soluble in water. So you're thinking ionic compounds and you're thinking polar covalent compounds. Okay. So nonpolar because it's tetrahedral, it's symmetrical. Nonpolar because it's a diatomic element, no electronegativity difference. And SiO2 would have the same shape as CO2, right? Silicon and carbon are in the same group. So if you remember that CO2 is linear and symmetrical, then SiO2 would be linear and symmetrical, so that's nonpolar. That leaves the one thing here, it's that. And remember, this is a covalent compound, but it's an organic compound, but anytime you have a functional group, that compound is now polar. So this would be a polar molecule. So it would be water soluble. Now, if you remember, when they write that OH there in an organic compound, they write that OH at the end of the formula. That's telling you have an alcohol. And alcohols are very water soluble. And the reason that is remember, the rule is like dissolves like. Water's polar, so other things that are polar should mix well with it. But the more alike you are in terms of intermolecular forces, the better you'll mix well. So since water's polar, but also has hydrogen bonding as its strongest IMF, alcohols, because they're polar and they also can hydrogen bond, that's going to make them even more water soluble. So alcohols are very water soluble because they're polar, but B, because they also can hydrogen bond like water can hydrogen bond. Okay. All right. 22. We're almost at the end. Thanks for bearing with me. All right. Which statement describes a non-electrolyte? So remember, non-electrolytes are things that dissolve in water, but they don't produce ions. So the resulting solution does not conduct electricity. Okay. So it's something that dissolves in water, but the resulting solution does not conduct electricity. That's what we're looking for. So when a non-electrolyte dissolves in water, the resulting solution does not conduct electric current. There you go. That's the one. Okay. All right. Hopefully, if it was an electrolyte, when it dissolves in water, the resulting solution would have ions in it, and then it would be able to conduct electricity. All right. But a non-electrolyte doesn't conduct electricity, but it still dissolves in water. Right? So something like an alcohol, you can dissolve an alcohol in water. It mixes very well with the water and forms a solution, but the resulting solution doesn't conduct electricity because the resulting solution doesn't have any ions in it. Okay. But sodium chloride, that mixes well with water. But when it dissolves, remember the sodium and the chloride separate into sodium ions and chloride ions, and that produces ions in solution, and that solution would conduct electricity. Okay. Weak electrolyte. Okay. So remember, ionic compounds are strong electrolytes, and the other strong electrolytes are strong acids. So if you're looking for a weak acid, if you're looking for a weak electrolyte, you're probably looking for a weak acid. Okay. So it's basically which of these compounds is a weak acid. Okay. Well, let's process of elimination. Okay. That's not an acid. It's not a salt. Okay. That's a sugar. That's not going to conduct electricity. That's an alcohol. That's not going to conduct electricity. So process of elimination got me to this thing. Now remember, we just went over a problem where if you see an organic compound and it says OH at the end of the formula, you should be thinking alcohol. But if you see OOH, that's a carboxylic acid. That's an acid. And carboxylic acids are weak acids, so they will produce ions in solution, but not as many as strong acids will. So they will be electrolytes, just not as strong. They'll be weak electrolytes. Okay. And I think I wrote some notes down here. Remember, that OOH, if I actually drew the structure of that molecule, that's the OOH. Remember, that functional group is the acid functional group for organic compounds. So this is an acid. It will produce some ions in solution. It's just not a strong acid, so it's not going to produce as many ions, so it's not going to be a strong electrolyte. It's going to be a weak electrolyte. Okay. And then we got two more. Here we go. All right. So we got hydrocarbons. So the minute I see hydrocarbons, it's organic compounds, but no functional groups. So remember, hydrocarbons, nonpolar. The only IMF that nonpolar things have are London dispersion forces. That's it. Okay. So hydrocarbons don't have hydrogen bonding. Cancel it out. They don't have dipole-dipole interactions. Cancel it out. Okay. Covalent bonds have nothing to do with separating molecules from one another, right? If this is a molecule and this is a molecule and they're attracted to each other, what's holding them together is an IMF, an intermolecular force, not a covalent bond. There's bonds within that molecule, okay? But to separate this molecule from that molecule, all I have to break is the IMF connecting. And the only IMF that nonpolar molecules have is London dispersion. And remember, London dispersion gets stronger the longer the molecule, the bigger the molecule, the bigger the electron cloud of the molecule, the more polarizable it is. Okay, that's really what London dispersion describes. You know, what are the odds that I get a random distribution of electrons within my cloud? Well, if my cloud's small, I don't have high odds, but the longer my cloud gets, the more chance of an uneven distribution of electrons, which is what London dispersion is, okay? And notice that, like octane has a higher boiling point than water. What does that mean? It means the London dispersion forces between octane molecules is stronger than the hydrogen bonding between water molecules, okay? And that's because octane is 8 carbons long, right? It's a big molecule. So London dispersion, as long as you get big enough with a lot of electrons, you can have stronger London dispersion than a dipole-dipole interaction or a hydrogen bond, okay? But here we're just comparing different London dispersion forces, okay? Excuse me. Last one, molar mass of carbon dioxide. You should have that memorized, 44, right? But, right, what do we have to do? We got to get the right formula. So we have to know that carbon dioxide is 1 carbon, 2 oxygens. We go to our periodic table. 1 carbon is 12.01. Each oxygen is 16. We add everything up and we get 44.01. They rounded, so 44 grams per mole. Remember, the units for molar mass are grams per mole. So 44 grams of CO2 is equal to 1 mole of CO2. That's what molar mass tells you. Okay? All right, that did it. All right, so hopefully that answered any of your questions you had in this practice assessment. Now go give this one a try.